Hi everyone, welcome you all to CNCF on-demand sessions. Today we'll be discussing about cloud-native inference at scale, specifically talking about LLM deployments with KServe. I am Snelata, member of technical staff at Nutanix.
Hi, I'm Jay. I'm a member of technical staff at Nutanix, and today I want to talk about KServe. KServe is an open source CNCF incubating project. It provides a Kubernetes custom resource definition for serving ML models on arbitrary frameworks, encapsulating complexity of autoscaling, networking, health checking, and server configuration to bring cutting edge serving features to your ML deployments. It provides a unified platform for both generative and predictive AI inference on Kubernetes. Today we'll be focusing on generative AI inference on Kubernetes. So to talk about KServe architecture in brief, there are two parts to it. We'll talk about the control plane first, and then we'll talk about the data plane. The control plane is the brain of the KServe platform, managing the lifecycle of the inference service, coordinating with the Kubernetes API. It operates independently from the data plane, allowing for clean separation of concerns and improved system reliability. The data plane supports API protocols for generative models based on OpenAI API specification, which has become the de facto standard for large language model inference. Example includes V1 chat completions, V1 chat, and V1 embeddings. So let's talk about the KServe architecture with the help of a brief diagram. The KServe controller is responsible for watching KServe resources as well as gateway API resources. An example of a gateway API resource is an HTTP route, whereas an example of a KServe resource is an inference service. Whenever an inference service resource is created, we create a Kubernetes deployment, which in turn creates a Kubernetes pod. The pod is responsible for running the model server instance. We can configure the arguments that is passed to this model server pod, therefore allowing us to configure how this pod behaves at runtime. KServe allows us to use autoscalers, for example, KIDA or HPA or Knative, which allows us to increase or decrease the number of replicas of our pod at runtime. Furthermore, with the help of a local model controller, we can create processing volume claims in which we can store model instances which can be cached across multiple deployments. When an HTTP route is created, the gateway is able to directly send the traffic from the gateway to the model server pod, allowing users to inference directly. So this is a very brief architecture of how KServe works. Now we'll look at a very small demo of inference service. Hi, today we'll be talking about KServe's Inference Service CRD. This allows us to deploy large language models onto our Kubernetes cluster. We'll use the Quen model, which is capable of understanding and generating human-like text across multiple languages. We'll create a namespace called KServe test, where we'll be deploying all of our resources. Second, we'll create an inference service CR, which will be used to deploy the LLM model. This is the model that we're deploying, and we've also specified the requests and limits that has been provided to the pod being created. We'll be serving the model under name Quen. If we were to access gated models, we'd require Hugging Face tokens, and a corresponding cluster storage container resource also has to be created. Let's jump right into the example. So here we have our inference service CR. So if we were to fetch our inference service CR, we can see that a Quen LLM inference service has been created and it is ready. If we look at the pods in the KServe test namespace, we can see that a pod called Quen LLM predictor is ready. It is running right now. Now, in order to hit this particular pod, we will have to go through the gateway. What I've done is I port forward the gateway onto my local node on the port 8080. So if I were to hit localhost 8080 along with the chat completions request presented here, I'll be able to interact with my model. Let's run a sample request. As we can see, we've hit the model service and we have received this particular response. We have sent a total of 186 tokens along with 150 that was generated and 36 was the input number of tokens. This is how we can interact with the KServe Inference Service CRD.
So far, we have been discussing about how inferencing happens with KServe via inference service CRs. Though there has been a lot of recent improvements in the inferencing space, and let's try picking up one at a time to see how inferencing paradigm looks like at recent days. Starting off with intelligent routing. Intelligent routing was brought into concept by Gateway Inference Extension, an official Kubernetes project. It was meant to brought with a vision in order to standardize the way we see routing of inferencing, or we can say GenAI workloads on the Kubernetes ecosystem. Though still now, whenever we talk about Kubernetes way of hosting models, we generally used to rely on queue proxy load balancing, or we can say the layman round robin and random routing logic in order to route requests to. But idealistically, that's not the right way to do the same. GI brought in the concept of introducing features like model-aware routing, where we could specifically set which model we want our request routed to. Allows priority serving, wherein it gives us the configurability to set priority levels to inferencing requests and address them accordingly. It also allows customizable load balancing, offering model server level aware load balancing that reduces latency and optimize our throughput. Also optimizes our hardware usage, which is inherently the most important goal of any inferencing ecosystem that utilizes any of the GPU hardwares. Moving forward, let's dive into GI scheduler architecture. GI's architecture's main component is EPP, the endpoint picker, that has a task in order to determine which of the endpoint or which of the model instance is the most appropriate in order to serve a given inferencing request. Understanding the traffic flow, we have taken an example of Envoy Gateway. Imagine a request did hit the Envoy Gateway and then reach the EPP pod. EPP pod then utilizes filters, scores, and scrapers in order to evaluate all the model instances that are tied to inference pool GI CRD. Inference pool GI CRD, let's just talk about what inference pool GI CRD looks like. Inference pool GI CRD primarily is a CR that encapsulates all the model instances. It acts as a label to what all instances belong to a specific pool that the EPP would take in order to evaluate the model instances. While scrapers, filters, and scorers is from the EPP component utilizes metrics from this pool, filters them on a user set configuration, and at the end scores them on the basis of the KV cache they score, the sessions, the GPU utilization. Maybe when we talk about advanced configurability on the scorer side, we can look specifically on the queue length and other metrics in order to identify what exactly is the most optimal pod for a given inference request. This information is then forwarded back to the EPP, and the EPP forwards the information back to the gateway. Gateway now at this point receives the pod IP, not the cluster SVC URLs of any of the model instance, but specifically the model instance pod IP where the request has to route it to. Let's talk about a second feature in the set. Disaggregated serving, more to be cited to as a feature, it is primarily a serving style that redefines the way we see inferencing. Initially, the collocated setup was the only preferred system when inferencing came into play. But as we grew far, as we realized the shortcomings of the traditional serving style, we came to realize that in the traditional serving, the main two operations that takes place fulfill and decode, which are the main process in any of the inferencing ecosystem, inherently has a shortcoming that the decode operation has to await on the prefill to happen first, and while the prefill is being happening, the decode operation is at halt altogether because of the GPU being tainted by the compute bound process already happening. This shortcoming was dealt by bringing up disaggregated serving that separates these two operations into two separate nodes altogether, where one GPU node only deals with the prefill operation, while the other deals with doing only the decode operation. Whilst when we do separate these compute and memory bound operations differently, when we treat them differently, it does not allow it does allow these two when we do separate these two operations on different GPU nodes, it does allow us to do both of these operations simultaneously with the decode of the previous token of the previous inferencing request happening while the current request prefill is happening on yet another node. Thus, it adds to almost zero awaiting latency to the inferencing time. While we talk about disaggregated serving, KServe do provide disaggregated serving with the support of LLMD, a yet another open source project. Let's take a closer look on how disaggregated serving looks like. As you can see, whenever a request hits the controller forwards those requests to the prefill instances first, and then certainly post one request at a time. The KV cache are being transferred from prefill to decode, which which are utilized by the decode instances in order to auto-regressively generate next tokens. In this kind of ecosystem, we always tend out to do a prefill operation on the current ith request while doing a decode operation on I-1th request, and hence not adding any latency of the await state. Let's look into how LLM Inferencing Service CR for KServe looks like that allows us to do disaggregated serving. This feature is brought in with support from LLMD, yet another open source community. KServe encapsulates LLMD in order to provide disaggregated serving. In the inference service CR, if we take a closer look, there has been two different kind of workloads which we can put into the spec. First is the decode workload, where and the second is the prefill workload. This CR allows us to specifically set what replicas we want to have for our decode workloads and prefill workloads separately. So far, we have been discussing about the new set of feature that the KServe LLM Inference Service CR brought us. Let's take a keen look of how LLM Service CR looks like and what it all has to offer to us. The LLM Inference Service custom resource was brought specifically for GenAI and LLM workloads. It extends KServe's model serving capabilities to support large language models with flexible configuration and scaling. It simplifies LLM deployments. It integrates with Inference Gateway, allowing intelligent routing. It also encapsulates LLMD, allowing disaggregated serving. Let's take a closer look of how it does that. The LLM service controller creates all the gateway resources that are necessary to route, as well as provision the scheduler and model instance. Once a client request hits the gateway, it decides where the request should be routed to via the EPP pod. The inference scheduler, specifically the EPP pod, receives the request, which then decide which replica or the model instance is the best to serve a given request. The status of this entity, that which instance is the best, is forwarded back to the gateway by the scheduler. Then the request is forwarded to the specific model instance via gateway, and then the request output is streamed back to the client. As you can see, a visually represented pathway where user request is sent to the gateway API layer and then passed on to the inference scheduler, which looks into things like KV locality, KV usage, GPU utilization, and other stuffs in order to determine which of the model instance is the preferred instances of the request. As you can see in the downline, we have an LLM ISVC controller that is responsible for spawning up all the resources that we see on the bottom and the top. Let's try to understand the traffic flow when we are using the LLM Inference Service CRs. Whenever a new LLM request is being hit via client to the gateway forwards the request to the scheduler, the gateway extension EPP pod, which chooses the best model server on the basis of load, KV cache, GPU utilization, and other stuff. This pod is also responsible for fetching metrics from the model instance's bottom line with a configurable loop, which can be default set to 50 milliseconds. Post that, when it decides which is the idealistic model instance to serve, it routes a request to the specific model instance, it receives back the response and route the response back to the user. Easy and smart. Let's dive into a quick demo on how LLM Inference Service CRs provide us this configurability. We'll be talking about KServe's LLM Inference Service CRDs that allows us to deploy ML models on Kubernetes clusters. So far, we have discussed about many advanced features that are required in a modern optimal inferencing systems, like intelligent routing, disaggregated serving, and distributed inferencing. LLM Inference Service CRs encapsulate all of them in order to provide these features via KServe. Today, we'll be taking up an example to illustrate how intelligent routing is being done via this CR. We can follow up the talk in order to understand what are the prerequisites for this. So, we would be first needing to create a namespace, KServe test. Secondly, we would be creating a gateway which would facilitate sending a request to the underneath system. Third, we would be creating an endpoint picker, which is one of the essential components when it comes to intelligent routing. Endpoint picker primarily encapsulates one of the most important components like plugin, profile handlers, and picker that allows us to identify which is the most optimal model instance that should serve a given inferencing request. Looking at the config, we can realize that we have plugins like prefix cache excluder that looks to the prefix of the inference request in order to identify which pod has which prefix and which pod should address to a given inferencing request. Similarly, we have other plugins. We would be needing to create the same, and here we could see LLM Inference Service config. This is a default config in case we do not provide any of the values while creating LLM Inference Service, which we would be seeing somewhere here. It would fetch the default values from the config. So yeah, this is the LLM Inference Service config, which is the main component of the KServe facilitating this particular feature underneath. We will be using a Qwen 0.5 billion instruct model today. And yeah, here as we can see, it has a reference to the base LLM inference config that we just saw above. An AI gateway route that acts as a bridge between AI gateway and our EPP pod. It also has a backend target to our inference pool, which we can see here, so that it allows us to send a request to specific model instances that is being populated to it via EPP pods. Just to give a quick heads up on how an inference pool spec looks like, we'll be taking a look at it. As we can see, we have the inference pool name here and a same endpoint picker ref here, which was the name of the EPP service we would be creating. Yeah, just to get back, we would be needing to create this AI gateway route, yeah, including the inference pool and as a backend ref. There is one more additional feature that we could have known as rate limiting. Rate limiting allows us to set usage level restriction on a certain user. For example, we could be setting what number of tokens a certain user can utilize for a certain model. So yeah, this is how the spec looks like. Today, for the sake of simplicity, we would be skipping it. Let's get straight to the working. So yeah, just to save up a little time, I have pre-installed everything, including the model CRs and EPP pods. As we can look, I have already my model instances up in my KServe test namespace, including the EPP pod. I have my controller pod active in the default namespace, the LMICC controller. We can get started by port forwarding our gateway URL in order to send requests to. Let's get started. I have exported environment variable. Let's expose the same. Now let's try sending this mock request to. As we can see, our gateway is port forwarded. Let's try sending a request to. So yeah, we can see that we have received a successful output, including the total output tokens, our prompt token details, prompt tokens, and completion tokens. But we still could not see what actually happened at the backend. How did actually the intelligent routing took place? In order to see the same, we would be looking at the EPP pod in order to determine what were the suggestions that were taken place by it. For the EPP pod, cool. Let's check the pod's name. This is a pod name. Let's try checking the pod logs. Cool, it's the same pod name. As we can see, we have many logs here right now. Let's try sending a new request in order to observe if we have things like KV cache utilization that would confirm that both of our requests did hit the same pod. Cool. Let's try checking one of the pod prefix, one of the scorers that we did use. Cool. As you can see here, we have our prefix cache scorer somewhere here. Also, we can see here that our prefix cache scorer did execute it, including our load aware scorer. And next, we had our we had our picker login, in which we had the score of both of our pod, which are there, the model instances VLLM pods. One of our pod with this pod IP was scored a 0.5, while the other pod got a pod score of 2.5, which had this address. And next, our final picker that ran, which selected a maximum of one pod out of the two candidates available, sorted by maximum score, which confirms our implementation that how our EPP selects optimally one pod and route the pod IP back to the gateway, and the gateway then routes particular inference request to a specific pod. Thank you. That's all we had today. Just want to give a huge shout out to Nutanix Kubernetes platform that we have utilized today in order to run all our demos. It's a simplified platform to run and create Kubernetes clusters. Feel free to follow the link for a quick test drive. Thank you. Have a good day.